those of us who think about space sometimes really don't grasp the enormity of it, and it's very difficult. Well, Bob Vanderbei here, he and his co-authors have created a really cool visual tool / book to help us kind of see the enormity. Bob, why don't you show us what I'm trying to describe?
Here's the book. And when you open the book up, the back of the book has another little piece that opens up out of it, so that now we have it like this. And this back piece has lenses in it for like glasses. And so I can take off these glasses. I can put this up here, and then I can flip, hold on. I can look, and wow, I am seeing the Crab Nebula in 3D right now. And it's just amazing. And now if I show it to you, this is how it looks in the book. But when you look at it through the glasses, your one eye sees your left eye sees the image on the left, your right eye sees the image on the right, and your brain just sees one thing as a 3D thing because your left eye and your right eye are seeing it, and it's slightly different. These two pictures that you're seeing here are not identical. They're a little bit different. And so if you can tell your one eye to see, your left eye to see the left image and your right eye to see the right image, then your brain sees it as a 3D object. And so the book has, I think, about 70 of these things, a whole bunch of them, all kinds of different stuff. And there's Mars, there's something.
Yeah, I think
moon. Oh, there's an
astronaut. That's a wild picture.
Yeah. And that's the back of the moon. The front of the moon, if I could get this thing to give me one page at a time. There we go.
Okay, so there's the moon.
Pictures of the moon. Yeah. So you wanted to discuss how I get these pictures.
Yeah, because tell us a little bit about, that our eyes have certain separation for vision, but when you're looking a long ways away like this, what happened?
Right. So, I mean, just to go briefly close by, if I hold my finger up and then I close my one eye, the finger looks like it's over there, and I close the other eye and the finger looks like it's over there relative to the stuff in the behind. And so that's how we see 3D, is our brain interprets that trend, that translation left and right when our eye sees the two things differently. And so how do we do that on a cosmic scale is, I think, the question, and that's very interesting. And so let me start with just the moon that I just showed you. The moon orbits the Earth, and the moon is in this locked scenario where we see the same side all the time. One day on the moon is equal to 1 month on the moon. The time it takes to rotate around once is the time it takes to orbit around once. So we're always looking at the Earth side of the moon. And so the simple thing would be, well, then that's boring. That's like nothing happening. But here's the interesting part. It's not a perfectly circular orbit, the moon, around the Earth. It's slightly eccentric or elliptical orbit.
Okay.
So sometimes it's a little bit closer and sometimes it's a little bit further, but the rotation doesn't change. The orbit changes a little bit.
Okay.
I mean, it's consistent 1 month after the next.
Right, but it's elliptical instead of a
instead of a
circular,
perfect
which is
circle. Right. And so if you take two pictures of a full moon, you might be taking them at different parts in this elliptical orbit, and therefore sometimes it speeds up a little bit, and sometimes it's a little bit ahead of the game, sometimes it's a little bit behind the game. And so when you look at the moon, it's not, just to the average person who looks up at the moon, they say, it looks exactly the same as it's always looked all my life.
Yeah.
But the reality is it wobbles a little bit back and forth from 1 month to the next when you look at the full moon. And so you can just take two pictures of the full moon and then just put them into your favorite picture editing program, Photoshop or whatever you like, And you can realize, oh, they're not exactly the same. This one looks more like the left eye would see it. This one looks more like the right eye would see it. Oh, and you might have to actually rotate them a little bit to make sure that the translation is purely left and right. And because, when you take your picture, your camera might not have been exactly right. So there's always a little bit of image processing, tinkering with things to get the effect exactly right. But yet you can do this. And that's how that picture was, how that parapet
It was just different times, though, based on where it was in its orbit then.
Yes. And so,
Very
so sometimes
clever.
that rotation's a little bit ahead of things, and sometimes that rotation's a little bit behind things because the speed at which it goes around is not a constant speed. So, yeah.
Now, you mentioned another one, though, where you actually did some physical separation between the cameras, I think. You mentioned that.
Yes. Oh, yes. So, what I just described to you was only the very first picture in the book. I've taken pictures of the Venus transit. Are you familiar with the Venus transit?
No, I'm pretty ignorant. So.
Can you see? That's the sun.
Yeah, I can see the prominent dot.
That's Venus. Because Venus's orbit is closer to the sun than our orbit. And so most orbits, when Venus passes the sun relative to our perspective, usually it's above the sun a little bit or below the sun a little bit, because our orbits in our solar system are not all exactly in the same plane. So all the planets orbits with a slight tilt in their angle of the plane of that orbit is a little bit different from the plane of this orbit. And so usually when Venus crosses by where the sun is, it's either above or below, but not always. And these are exciting events called Venus transits. There was a Venus transit back in 2004, which I took pictures of. There was a Venus transit in 2012, which I think were the pictures I just showed you. And the next Venus transit is like 70 years in the future. So
my gosh.
You and I probably won't be here to see the next Venus transit. But you were asking about measuring things from two different positions. That picture I just showed you, the Venus transit, I took one of those pictures. A friend of mine who lives here in Princeton, New Jersey, he got on an airplane and flew all the way to Hawaii for the Venus transit because the predicted weather would be better there. He could go up on top of Haleakala, I think is where he went, the mountain on Maui. And so after this whole thing was over, he and I compared notes, and it turns out that he had a picture taken at exactly the same, we had multiples of these, but we had pictures taken exactly the same second. Here I am in New Jersey, there he is in Hawaii. This is, I forget how many thousands of miles apart, but we're taking a picture of the same thing from two different perspectives here on Earth. And Venus is, on a cosmological scale, is not very far away. So just two different perspectives from here on Earth is enough to see, oh, it's closer to us than the sun. And so if you look at that through the stereo viewer in our book, you see, oh, that little black spot there is not on the sun, it's in front of the sun. It's some dark blob in front of the sun. That's Venus. And it's dark, of course, because we're seeing the backside of Venus. It's not getting any light shining.
Oh, yeah, right. So how neat.
Yeah.
And so, you brought up, we probably won't be here for the next Venus transit, but I'm thinking my great nephew will be. And I'm thinking, even though he's not even 2, that this book could actually be really fascinating for him, as well as someone who's 98. Tell us a little bit about the motivation for the book. What was the motivation?
A love of astronomy in general. And I like 3D stuff in general, and even before this book. Different people are different. When I look at my finger up here, I'm looking at my screen, and when I hold my finger up, I actually see 2 fingers, even though I'm holding one up. Because the left eye sees one, and the right eye sees the other. When both eyes are open, I see 2 things. A lot of people, their brain kind of blanks one of them out. They're right eye dominant or left eye dominant. And even though they do see things as 3-dimensional when the perturbations are small, they don't really see it as two separate things when it's a dramatic
You
like that.
actually see two separate things?
Yes, I'm seeing two fingers right now.
Wow.
And so so I've always, and I don't know what fraction of people their eyes and brains are like that. I think it's a pretty small subset, but I've always been very interested in this 3D thing because I can sort of appreciate it in a different way, in a more detailed way. So I've always been interested in 3D stuff, and I've always been interested in astronomy, and so combining the two seemed like a really fun project. And there's 4 authors. I'm one of them. The other 3 authors on the book are, let's see if I can point. Is that J. Richard Gott?
Yes, exactly.
Michael Strauss.
That's you.
And is that
Michael
Neil deGrasse?
Strauss? It is.
And that's Neil deGrasse Tyson. So yeah. Oh yeah, there's Michael Strauss. So
how did you guys come up with the concept?
So to give you a little bit of the history, the 3 of them, not me, the other 3, for several years co-taught a course here at Princeton, an introductory astro course. And they taught it for many years, the 3 of them co-teaching it. And then at some point they thought we should write a textbook or a book to use for this course. And so they wrote a book called Welcome to the Universe and published by Princeton University Press, which is right in that next building over there. You can't see it, but I can. And so they wrote this textbook, and then they wrote a problem book to go with the textbook, and then they wrote a shorter version of the book. And so they've been doing this Welcome to the Universe stuff for several years. And I wrote a book with J. Richard Gott, one of the authors, another book called Sizing Up the Universe, which is a book about how do we know how far away things are and how big things are. And so it really is all about this kind of 3D perspective. Not only did I make a picture of that Venus transit, I used that information to measure how far away Venus is from the Earth. By knowing how far away in miles that friend of mine was in Hawaii, and the angular translation that it was in these 2 pictures, I was able to figure out how far away Venus is and get basically the right answer. So being kind of a mathematician with an interest in astronomy, all these kinds of things come together, and it's really, really fun. So the moon, because it wobbles, Venus, because 2 different places on the Earth taking pictures. If we go a little bit further out, nearby stars, they're so far away that if my friend's in Hawaii looking at a star, and I'm in New Jersey looking at a star, and we take a picture of the night sky at the same moment in time, our pictures are going to look the same, even though technically speaking, they're not. If we could measure this to a really, 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 really tiny angular separations, we would be able to see, but we can't. Okay, but here's the fun thing. The Earth goes around the sun once a year. So if I could take a picture of a place in the sky where there's a nearby star over at this part of our orbit, and then 6 months later when we're over here, take a picture of the same area of the sky, all the far away stars will look like they haven't moved, but the nearby ones, or the nearby 1 or 2 in the picture, will look like they've moved. And there's a picture of that in the book too, or should I could find it on my webpage.
Yeah. You sent me the webpage, yeah. Anyway, but yeah, that's interesting. So while you're looking for it, so it gives you that separation, the fact that the Earth has gone around the orbit, and here it is.
Yeah, and I found it really quickly. So it's a little bit hard to tell that there's a difference, but that bright star there is called Barnard's star, and it actually is a little bit displaced left and right relative to all the other stars in this picture. And if you look at it through the stereo glasses, you'll see it. It looks like it's in front of the picture. And by the way, that is how astronomers measure the distance to nearby stars. That angular translation back and forth over the 6-month period is called the parallax. The parallax is a number. It's given in what's called arc seconds. I'm not sure how many of the viewers know what an arc second is, so I'll tell you. A circle has 360 degrees. I think pretty much everybody knows that. 1 degree is broken up into 60 little smaller pieces. They're called arc minutes. 60 minutes in an hour, 60 arc minutes in a degree. 60 is the relevant fraction here, or 1/60th. And if you break an arc minute up into 60 smaller pieces, that's called an arc second. And so that's 1/3600th of a degree is an arc second.
Okay.
But measuring that displacement back and forth in the distance is, well, sorry, not the distance, the parallax it's called. The parallax is given in arc seconds, and the number is usually smaller than 1. Okay. And for some nearby things, like the one I just showed you, Barnard's star, it's, I think, about 2 arc seconds displacement over the course of 6 months. And so that's a small number. The size of the moon, when we look at the moon in the sky, it's a half a degree. That's 1,800 arc seconds. So we're talking about a displacement that's about 1,000th of the diameter of the moon as we view it. So we're talking about small things, but with modern telescopes, even my telescope that I have at my house, I can measure things down to maybe about a half an arc second or a tenth of an arc second, something in that realm. So for nearby stars, with my equipment on my driveway, I measured the distance to Barnard's star with pictures I took of Barnard's star and get an answer that's, within 10 or 20%, I forget exactly, of the right answer. This is what astronomers have been doing for like 100 years. This is how they identify how far away the stars are. They look for this parallax. And by the way, one of the measures of the distance, because nearby ones have large parallax, far away ones have small parallax. So parallax is kind of the opposite of distance. And so there's something called, the distance is called parsecs, and that's the reciprocal. If the parallax is 2 arc seconds, then it's a half a parsec away. You take the reciprocal of the number. And that's one of the ways that astronomers measure the distance to thousands of relatively nearby stars, and they give the distance in parsecs. There's this called this distance ladder, various ways of measuring things further and further away. In fact, I like to joke, with people and say, well, the sun, we could measure the angular displacement in the sun 6 months apart. Oh, it was over there, now it's over there. The parallax of the sun is 180 degrees, which we then have to multiply the right number to get that into arc seconds, which would be a huge parallax.
Yeah. I was impressed in your website. You've got a link to a calculation that measures, I think you end up measuring your height compared to the sun going down and the sun coming up, and you kind of determine that it's, the Earth is round, I guess, was one of the things.
Yes. I did measure the size of the Earth, and it was pure luck, actually. I'm from Michigan. I go visit relatives frequently, or at least once a year these days. And I have a cousin who used to have a house on Lake Michigan. And we would go and have dinner at my cousin's house. And I was there once, and this is like 15 years ago. And we were there for dinner. And then after dinner, oh, look, the sun is setting over Lake Michigan. Because Michigan, looking at Lake Michigan, you're looking west. So you're seeing the sunset. And and it was beautiful because the sky was clear, and Lake Michigan, there was no wind that day. And unlike the Atlantic Ocean and the Pacific Ocean, when you go to the coast, there's always waves coming in because there's tide and all kinds of stuff. But Lake Michigan, even though it's a big lake, you can't see the other side. You're just seeing water up over to the horizon.
Right.
Yeah, and but it doesn't have, if there's no wind, it can be very smooth. And so it was beautiful sunset, no waves, and I ran and got a camera. Wasn't planning to do this. Took a bunch of pictures of the sun setting on Lake Michigan. And then I look at the picture and I'm like, oh, that's interesting. I was literally just a minute or two after I took these pictures, and I'm just looking at these pictures on the little screen on the back of this camera. And I, zoom in like I always do on these things. And I'm like, wow, there were two things that were amazing to me. One, usually when you can Google sunset or sunrise pictures, there's thousands of them, and they all show this big streamy thing because of the waves. The waves distort, reflect the sunlight, and you just get this kind of this stream of light along the lake or the ocean between you and the sun. And there was no stream. So that was the first thing. Like, wow, that's really interesting, because the water was so smooth. There were no waves, no significant waves. And then, so that's when I zoomed way in, and then I'm like, wow, here's the horizon, here's the sun. It's like 2/3 set, only 1/3 above, and here's its reflection. And the reflection looked beautiful. There's the sun, there's its reflection below on the water. And when I looked at that closely, I'm like, but wait a minute. The reflected one is smaller in height than the actual sun. And it took me like a minute or two, or maybe 5 or 10, I don't remember, to realize, oh, that actually makes sense. If the Earth were flat, Lake Michigan would just be a perfect mirror. But because the Earth is a sphere, the surface of Lake Michigan is not flat, even though it kind of looks flat to us. It's not flat. And I spent the next week of my time doing the trigonometry and some geometry and getting out my calculator to compute stuff. And I had to estimate how high I was standing above the water, because I didn't measure this. I just and I was no longer at the beach when I was doing this. But I figured, well, I'm going to hold a camera up. It's about 5'6" above my feet, but I'm standing on the sand, maybe a foot above the water. I didn't know exactly how high I was. So I took a guess, let's say 7 feet. And so using that height measurement together with how much compression there was, I was able to measure the size of the Earth. And again, got an answer that was right to about 10 or 20% of the right answer. So.
And I think the thing that comes through that in your book is just the fun, love you have and bringing it to other people. Yeah,
it really is fun. And that became a published paper, actually, that measure of the size of the Earth from a sunset picture. And by the way, maybe another thing I'll mention briefly is, how do we know the Earth is round, first of all? And that's another interesting and important thing. And that is actually explained in the book. How do we know the Earth is round? A sphere. And because you just go look around, it doesn't look like a sphere, it looks flat.
Yeah.
But you look at a partial lunar eclipse. A lunar eclipse. That's where the Earth is blocking the sunlight and you're not seeing the entire full moon. So, early in the evening, it was a full moon. It was beautiful, full moon. The moon's up there, the sun's opposite direction. And nobody even has to tell you that we are seeing the shadow of the Earth. And I like to say, 100,000 years ago, there were people on Earth. There were Homo sapiens, people just like you and me. But they didn't go to school. They didn't go to college. They didn't maybe even have a language to express themselves in a very detailed way. But they did have brains, which were biologically just as good as yours and mine. And they just lived in a different environment than what we grew up in. But they were just as capable of thinking and seeing. The resolution of their eyes was just as good. And they mostly lived outdoors, by the way. And there's a lunar eclipse every year or so. And so most people probably saw many lunar eclipses in their lifetime back 100,000 years ago. And it doesn't take that much cognitive skill to realize, oh, I'm seeing this weird thing, but it was just a full moon a second ago, or a minute ago, or an hour ago. and the moon rose over there when the sun set over there, and they kind of go around at the same speed. That's maybe our shadow. I think thousands of people, maybe millions of people, maybe not billions of people, over the course of a few 100,000 years when people existed on Earth, had exactly that logical thought. They may not have thought it in English,
Mhm.
but whatever kind of way they express things in their brain, they looked at it and realized that's our shadow. And when you see a partial lunar eclipse, you see a shape, and the shape looks like, I mean, the Earth is bigger than the moon, so you're not seeing the entire circle, but you're seeing something that looks
Yeah.
round. And then you see multiple ones of these over the course of your lifetime. Maybe some people saw 10 or 20 of them in their lifetime, and you're seeing them in different perspectives. Sometimes it was in the west, sometimes it was in the east, sometimes it was almost straight overhead, and it always looks round. Well, the only thing that has a round shadow, no matter which way you shine a light on it, is a sphere. I mean, I really think that many, 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 many people, thousands and thousands of years ago, made that logical deduction. But they don't get credit for it because they didn't publish a paper.
And they didn't have that camera to capture Lake Michigan at the right time.
Yeah.
Well, and again, I just think your book would be something that, could be good for a 2-year-old or for any age, really. But what sort of, has it been out there? Have you gotten any feedback from various age groups yet?
I haven't gotten feedback from different age groups because it just came out 2 days ago. So I have my copy and I've showed it to friends, but I haven't shown it to any 2-year-olds yet.
Yeah, okay, well, wait, and I'll let you know.
Yeah, let me know. But yeah, it's become very popular. When Neil deGrasse Tyson showed it on Colbert show 2 nights ago, and it went, or was it 3 nights ago? Whatever it was, Tuesday night. It went viral. It was #1 on Amazon. Of all books, it was #1 until this morning. It went to #2.
Well, he also was doing the reading too, right?
Yeah. And so if you go to the webpage, if you go to the Princeton University Press webpage and search for the book "Welcome to the Universe in 3D," you'll get to a webpage where he will narrate every caption on every picture. You can just be sitting here like this, and you got your computer that's reading to you, because the captions are on this half.
Yeah.
When I'm looking through it, I can't read the captions. I got to take it off, read the caption, then put it on, look at it, read the next caption, look at it. Or you can just go to the webpage and Neil deGrasse Tyson reads the caption for the first picture. And then you just have to flip to the next page and he reads the caption and he just reads the whole thing.
And he's got such a great reading voice. I mean, that's
he does.
That's a terrific combination. And again, it gets back to that thing of, as a parent, it'd be a great way to keep, you wouldn't have to read to the youngster. You get that immersive experience. Do you see being able to, you put like an iPad on the other side of your 3D thing and then be able to have interactive or new images and stuff?
Yeah. So I thought you might ask that. So here's one of them on my cell phone.
Okay,
Mars.
yeah, I see it. Yep, Mars.
And you can put Mars in the book. I mean, you can put the cell phone in the book.
Yeah.
There's my, oops, you can't see it.
Oh, yeah,
There's my cell phone in the book.
Yep,
And then I can look at it through the glasses.
Yeah.
Oh, it's 3D. How cool is that?
Very
So
neat.
yeah, so we'll probably make more, and probably other people will make some as well, since people buy the book and other people can post on the web, look at my 3D picture through the book.
Well, that's terrific. Well, Bob, it's been great having you on the VOD TV, and good luck as this goes out. And I look forward to meeting you. Hopefully, I can meet you next month, or I guess it's June 2nd to June 4th, the Smart Driving Car Summit, the 5th annual.
Yeah.
I've been writing today.
Yeah.
Is that?
Yeah, I'll come look for you, and if I don't find you, come and knock on my door.
Excellent. Well, Bob, thank you.
Great. Thank you for doing this. This is really fun.